Yep.
Just equal forms. I feel like I have to get something wrong.
That one right there, C, 6C. 2 hours I've been higher on this stupid thing, but I eventually got it, but it's driving me insane.
All right, let's talk about the review for the exam real quick, which will take place on Thursday, right? So I think this is a pretty good indication of what to expect. This first integral is an improper type 2 integral, which was not on our on our previous exam. So it's improper type 2. And then we get to areas between curves, and I'm actually asking you on number 2 to find the area. So you gotta grind that entire answer out, right? So what you might want to do on the test, just set it up and then come back and finish it later. It's up to you. And then from there on, it's setting up integrals. So set up this integral that gives you the volume. You've got a region. You're rotating around these different axes and lines. And I told you to expect this. That's what it'll look like. I also ask you to put any drawings to support your integral formulas. Those are kind of like right or wrong problems, right? Like, I'm not asking you to evaluate the integral, but if you're missing you put x plus 2 instead of 2 plus, or no, that wouldn't matter. But x minus 2 instead of 2 minus x, and then that's wrong, So, I mean, I won't take it completely like 0, but since I'm not asking you to evaluate them, you really need to understand the setup. So make sure you're comfortable with that concept. And then I gave you a problem here with the cross sections, and I had you do equilateral triangles on this one. It could be a lot of different things, right? It could be semicircles. Square, semicircle, triangle, about the only thing I give you. And don't evaluate the integral, just set it up. And then what is this one? Surface area? Oh, that's an interesting problem, yeah. So that's a surface area problem. And for this one, I actually had you on the review do the whole thing. I'm not sure if I'll ask you to do that on the test. And then we get to chapter 8. I give you some sequences, and I ask you to get the formulas for these. So you have to come up with the A sub n's for these. This is kind of like that additional assignment I gave you, except I don't think these were as hard, were they?
C was hard.
C is probably the hardest one. But these two are, I'm not going to give you super hard ones on the test, but you should be able to, know how to create an alternating sequence. You should know, how to get evens and odds, or things that jump by 5, or powers of 2, or something like that. You should be able to recognize those sorts of things. And then the last part is, do these sequences converge or diverge? For all of these, you just have to take the limit as n goes to infinity on all of these. And different things happen, depending on the problem. You might have infinity over infinity, or you might need L'Hopital, you might need some other trick, maybe the squeeze theorem, perhaps. You also have the absolute value test thing. R to the n, that was another thing. We know this limit, n goes to infinity of r to the n, that will go to 0 if the absolute value of r is less than 1. That's in your notes. It's in the notes that I provide. I think that's how you could do this problem right here, is you could rewrite that in a way that it looks like 2/3 to a power, and then 2/3 is smaller than 1, and you could get that to work that way. And then this one, you can use properties of logs to turn that into a single log, because you have subtraction between 2 logs, turn it into 1 log. And then on the inside, you got some factorial stuff, and you can just use properties of factorials to cancel. I'm hoping that what you're doing is trying to figure out how to do all these problems, and then if you're having trouble on them, you reach out for help, or help each other out, or get tutoring or something. Yes?
One of the questions you had up above, I think it was like number 3, it was find the area under the curve.
Yeah.
So when I had worked out that problem, part of it just seemed easier to do with like basic triangle geometry. Do we have to show, like, if that was the work that we showed on the exam, would that be okay? Or
You need to use an integral.
the integral could be part of it, like In other words, can they be combined? Like, there's an integral in part of it, but then part of it's just basic, like triangle stuff.
So there's a give and a take here. The question is whether or not, because this region, when you draw it, there's some simple triangles in there, and so why not just use like formulas for areas of triangles instead of doing integration? I am giving you a simple region to make your life better,
Right.
not to circumvent the technique.
Yeah.
So I could give you a problem where you can't use that, so I would prefer you use the technique and the integration on the whole problem rather than using the triangle formulas because the problem happens to have a triangle in it. You know what I mean? Yeah. Okay. So, I mean, I'm available in my office this afternoon, right? And then also tomorrow, right? Tomorrow, 8:30 till 11, I believe, I'm in my office. And then I'm sure y'all have like group meetings or whatever. I don't know what y'all do, you know. I'm sure y'all do, right? Y'all have some sort of online thing where y'all are
We have a
talking. Discord, that's the sort of Discord.
in person.
Yeah, so.
I keep asking.
Yeah. So anyway, yeah. I think this exam, I mean, I don't know. What do you think? Does it seem like it's going to be, do you feel better about this one than you did exam 2? Like all the techniques of integration? Yeah? Okay. All right, well let's get moving. We are really behind in this class. I mean, it's depressing. All right, so last class we were trying to, in the last class we were trying to get into series, right? And we were talking about sigma notation, and we did one test. We had one test out of all those tests, right? We had established the very first test. It was the test for divergence. It basically says that if you have a series and you look at the sequence formula within the series, if that sequence formula, when you take its limit as n goes to infinity, if it goes to something other than 0, the series diverges. And if it goes to 0, the test fails and tells you nothing, and that means you have to do a different test. All right? That's all we have up to this point. When it comes to series, that's all we have. So now what we're going to do is we're going to move into our first look at a specific series. When it comes to series, generally speaking, series is a very abstract idea. You can have all types of different series. We're going to look at one specific type right now. It's a very famous type of series. It's called a geometric series. And to be a geometric series, the series has to look a certain way. Okay? It has to look exactly like something, which I'm not going to share with you yet. Let's just see an example of it and maybe try and wrap our heads around what's going on. So here's your first look at it. What I have here is a square, all right? And this is a 1 by 1 square, so 1 foot, whatever, by 1 foot. And what I'm going to do is I'm going to take half of this square and find the area of half of it. So if I just do half of that, right? Half, what's this area?
1 by 1 is 1.
It's 1 by half. 1 times a half is a half. So I have 1/2, right? 1/2. Boom, there. Okay, now what I'd like to do is add to that half of what was remaining. So this white area is what's remaining. I want half of that and add it to what we already have. So if you add the red now to this gray, we have 1/2 plus, this is now 1/4, right? So we do a half plus a fourth, 1/2 plus, notice a fourth is 1/2 squared, right? 1/2 squared is 1/4. So I do a half plus a fourth, and that's 3/4. Now let's keep going. Of what's remaining, I do half again. Half of that white is going to be that. So we have the gray plus the red plus the green. The green is half of that, right? So when you do half of a fourth, you get an eighth. So that's 1/2 plus a fourth plus an eighth. An eighth is 1/2 cubed. Is this making sense what's happening here? I just keep going now. All right? Notice what it's adding up to be. Right now we're at 7/8. When I go again, half of the half of the half of the half. What? Half of the half of that. So half of that green is that one. That's another, that's a 1/2 to the fourth power. That's 1/16, right? And now look what I've added up to be, 15/16. That's the decimal, right? And I keep doing this, right? Keep doing this. right? And I just keep going and going and going. And look at what it's converging to. Doesn't this sum of all of those, doesn't it seem like it's converging to a number, right? What? 1, right? Now, if I ever stop, I'm not at 1, right? I'm not saying that I'm ever going to get to 1. I'm just saying I'm getting closer and closer to 1, right? So what I've done here is I've made this where I can actually go further out. Let's go, that's like the first, what we're looking here is the first like 20 pieces. That's 20 of those little rectangles. Let's do 50 of them. And just keep your eye on this number right here in red as I keep adding more and more. Oh, now the computer's saying it's 1. It's not. The computer's rounding. So what I'm going to do is I'm going to have the computer give me more decimal places. All right? See? So now if I go, further out I go, look what's happening. See how I just keep on like locking in the 9s as I go further and further out? And let me go further. Oh, see, my computer thinks it's 1 again now, right? So I'm going to hold on, I want more decimals. Let's do 75 decimal places. And now I keep going, right? Keep going, keep going, keep going. Keep going, keep going, keep going, keep going, keep going. Right? And look at I'm 0.999999999, right? And just the further I go, I just get more 9999s, right? So we are getting closer and closer to 1. Never actually truly getting there, but converging, right? The sum is converging. The series is converging. Yeah? So that is your first example of a geometric series, all right? Let me back this up so my computer doesn't freak out. So that is this example right here. You can see it written out. What we did is we did 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus ... forever. And it looks like, right, that geometrically that sum is going to 1, converging to 1, right? Now the general formula. What is the generic like form of a geometric series? This is what a geometric series looks like. Ignore that for now. It's a number plus that same number in front of some other number r. These two are multiplied. Plus that same number a in front of that number r squared, and then that same number a in front of that number r cubed, and then keep going and going and going. So like the example I just gave you, right? It was, what, 1/2 plus 1/4, right, plus 1/8 plus 1/16. In order to write it in that form, I'd have to write it like this. 1/2, how do I want to do this? Hold on. This is not going to be nice. Let me get to that because I have to shift it. Just leave it like that for right now. Let's do another visualization of this. Okay, so I'm going to put over here off camera, I'm going to put what the series looks like. It's some number a in front of r to the n minus 1, and then here n equals 1 to infinity, which is a plus ar squared plus ar cubed plus forever. All geometric series look like this. All right, so look at a as being a constant. It never changes in the problem. It's always the same number the whole time. R is the thing that keeps getting raised to a power. So like with the 1x1 rectangle, we kept on doing a half, and then half of a half, and then half of a half, half. The 1/2 would have been the R there, all right? So what I'm having the computer do here is I'm able to adjust the value of A and adjust the value of R. So right here, this right here is the sequence. That's this, just plotting the dots. And then the blue is adding them up. We did this last class. I showed you the sequence alone, and then what happens when you start adding the sequence, the pieces of the sequence up. So right now, if I use A as 1 and R as a half, then notice that it looks like it converges. It actually looks like it converges to 2, right? That converges to 2. If I change R, let's make R smaller. Now R is 0.2. It still converges. Y'all see how that still converges there? But if I let r be bigger than 1, let's see what happens if I let r be bigger than 1. Something's going to happen here. You can see it starting to, oh, there we go. As soon as I got past 1, what happens? This thing takes off to infinity, right? The sum gets infinitely large. So there's this like threshold. If the r is less than 1, then we're going to get some sort of convergence with the geometric series. If r is bigger than 1, then we get divergence. Question? Yeah.
Like r is that all the time less than 1 or just
No.
less than a?
No, r is just some number. It can be bigger than 1 or less than 1. R dictates whether or not we have convergence or divergence. Okay, that's all we need to know about r is that it dictates that convergence or divergence. This is just to show you that it does, like visually. All right, so here's the big takeaway. And I thought about this today because we're so far behind in this class right now that whether or not I prove this to you or not. And I'm leaning towards not proving this, which would be a first for me to not actually prove this formula. But I have videos online of me doing the proof of this, so if you want to watch it, I think you should go back and watch it. Yes?
What would the video be called?
You know what? I'll send it to y'all. I'll send you the link directly to it. So for any geometric series that looks like this, which is a number plus a number times r times plus a number times r squared, blah, 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 this series will converge so long as the absolute value of the r is less than 1. So as long as that number that keeps getting raised to higher and higher powers, as long as the absolute value of it is less than 1, we will get convergence. And we actually can say exactly what it converges to. It will converge to this number. This is a number. This is a over 1 minus r. Normally I prove this, all right, but just time constraints, I'm not going to. Now, if the absolute value of r is bigger than or equal to 1, then we will have divergence. It'll diverge. So let's just get to an example. Let's do the one we just had. Okay. So example, does this converge or diverge? If it converges, what does it converge to? One half plus 1/4 plus 1/8 plus 1/16 plus dot, dot, dot. Now we know this converges to 1, right? Because I showed you the squares. Okay, we know it converges to 1, but let's prove that it does. So what I have to do right now is prove to you that this is a geometric series. I have to prove that to you. I have to somehow show you it's a geometric series, which means I have to make that look like this. Right? I've got to somehow get that and turn it into this. And if I turn it into this, then I can use the thing I just showed you, that if the absolute value of r is less than 1, it converges, and if the absolute value of r is bigger than 1, it diverges. Okay, so I'm going to first start writing this out like this. I'm going to say this is 1/2, to the 1, plus 1/2 to the 2, plus 1/2 to the 3. I think you get the idea, 1/2 to the 4, plus dot, dot, dot. So I have to see that, right? I have to recognize that pattern. And now what I'm going to do is convert it into sigma notation. And this is where you have to be able to create the formula that creates that, right? This is where you have to look at it, analyze what's going on, and say, all right, this can be rewritten as a sum, n equals 1 to infinity. And what I need to do is create the formula that would spit these out. So what's the formula? What is it? 1/2 to the n. 1/2 to the n, right? So if n is 1, that gives you 1/2. And then you do plus, and right, because this sigma means sum, right? We're going to add things up. Starting with n equals 1, plug 1 in here, we get that. Then you say plus, now you plug in 2. Then you plug in 3, then 4, then 5, right? That creates it, yes? All right, now from this, is this a geometric series? Does that look like this?
If A is a 1, then
If A is 1, yes, but there's something else. There's something else that's not right.
minus 1.
Yeah, so we need an A. We need a number out front, which you could argue right now that there's a 1 right here, right? You could argue right now that A is 1. But there's a problem that this is not an n minus 1, right? That's n minus 1 in the formula, right? So for these two to be the same, or for that to look like this, I need an n minus 1 up there, right? So now what I'm going to do is I'm going to make an n minus 1 appear. I'm going to force it to happen. And that means I'm going to do this. Something we've done before. I'm going to rewrite this as n minus 1 plus 1. Is that not the same as n?
Yeah.
Right? Now, and then you sit there and you go, why are you doing that, right? Why are you doing that? Because of the next step. Watch, 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 see what happens. This is just in my way. You have it over there. You see where I'm trying to get to, right? Trying to get to this. So now the next step is to realize that using properties of exponents, that's the same thing. Right? Isn't this the same thing? If you have 1/2 to the n minus 1 times 1/2 to the 1, wouldn't you just put these together and add the exponents together? But I'm doing it backwards. I'm doing this, and I'm pulling it apart into two pieces. The first piece is this to the n minus 1, and the other piece is this to the 1 power. You see? Everyone see that? Now, this is just 1/2, right? I'm going to push that in front of this piece, so I'm going to put 1/2 in front here, and then I have 1/2 to the n minus 1. Now that is geometric. You've got A, you've got R, you've got n minus 1. See it all?
Does
Yeah.
the index need to be the same to?
This has to be a 1 for it to be, well, for us to use the formula for what it converges to.
Right.
Yeah, if this was n equals 3, you could still say it's geometric, but it would converge to something else. Okay, so everyone got it? We have the geometric form that we need, and now what we need to do is check, let's see, what's A, what's R. So for us, A right now is 1/2, right? And the R for us is 1/2 as well, right? 1/2? Now, if we take the absolute value of R, that's the absolute value of 1/2, do you all agree that's less than 1? Right? Why am I checking the absolute value? Why am I looking at the absolute value of R? Why am I doing that?
We have to have that in order. Because the way you showed us, like, graph.
Yeah, what I showed you here, right here, this formula, this master formula that we're going to use, is that if we ever see something like that, then I can tell you whether or not it converges or diverges by simply knowing what R is. If the absolute value of R is less than 1, we will converge to this. If the absolute value of R is greater than 1, we will diverge. By the way, this is on your sheets. If you go look at your sheets, you'll see it. And make sure you have that. Where the heck is it? Here we go. I have too much shit up here. All right, there it is. The one that says geometric series, right? See it? It says, if you ever see a series like this, right? If you ever see this, then it will converge, and the sum of that series will be A over 1 minus R as long as the absolute value of R is less than 1. Now, if the absolute value of R is greater than or equal to 1, then you diverge. That's it, right? So that's why I'm checking right now. I first had to identify what R was, right? And then take the absolute value, make sure it's less than 1. This tells me I converge, right? Not only do I know it converges, I know it goes to what? A over 1 minus R, right? A over 1 minus R is what it converges to. So I'm ready to actually give you the answer, right? Like this converges, so this, right, this, this converges, this sum, I'm going to write it this way. The sum n equals 1 to infinity of 1/2 times 1/2 to the n minus 1, that converges to a, what's a? 1/2 over 1 minus 1/2. But 1 minus 1/2 is 1/2, and 1/2 over 1/2 is 1. So it converges to 1, which is what we thought it would do looking at the geometric thing we did a second ago with the squares. Yes?
So for this test, unlike the first one, like it'll tell you if it converges or diverges.
That's right.
But like I assume the problem is that you can't use this for like,
Yeah, not every series is geometric, right? Geometric series have to be a certain way. So the end term test, the test we learned at the end of class last time, it only tells you whether or not you diverge, right? That's it. And then if that test fails, then you hope that it's geometric, right? If it's geometric, you will be able to say whether or not it diverges or converges. You will have a conclusive answer because you'll be able to determine what R is. And once you know R, you know everything.
so if it passes the first test and it does say it will diverge, like it'll tell you that it diverges if you were to use this one as well, right?
Yes, absolutely. Yes.
So how do you tell like a series is geometric? Like, what's the sign?
You have to be able to get it to look like this. The main characteristic of a geometric series, the thing that gives it away, is the R to the n. This right here is always just higher and higher powers of some number, right? We had 1/2, 1/2 squared, 1/2 cubed, 1/2. So it's just higher and higher powers. That's the giveaway, all right? Let's do another example, yeah? I kind of like not doing the proof. I mean, it's a beautiful proof. It really is beautiful, but
Want us to label that we use the geometric
yeah, so you should probably state, because we're going to have, when you take your final, right, at some point, when you take the final, when you're doing these tests, you're going to need to say, okay, I'm doing n-term test. Oh, that failed. Okay, I'm going to geometric series. Boom, right? That way, because there's so many different tests, you might go down one road, another student might go down another road. I need to be able to follow your thoughts, right? All right, so now, I should also point out that we're going to study a lot of different series here. The geometric is one type. If a geometric series converges, we can actually find the sum, right? A over 1 minus R. We can actually find what it adds up to be. There are only 2 series in this class. There are only 2 series that we can actually find the sums of. Geometric, and then another type that we're going to study hopefully today called telescopic. Other than that, all we can ever do with series is say whether or not they converge or diverge. That's it. I mean, in this class, I mean, it's a hard thing in general to find what a series converges or whether or not it converges or diverges. It's a harder question in general to find the actual sum of a convergence series, just generally speaking. All right. Boom, 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 boom. All right, more examples. Let's do that one right there. Does this geometric series converge or diverge? If so, find its sum. This is like the first basic example. Does that look like a geometric series to you?
Yes.
Yes. I mean, I've just laid it out exactly the way it appears on the formula sheet, right? What's A? 4. What's R? 3 over 2, right? So this is exactly that form right there. So A here is 4, R is 3 over 2. And then I check, what's the absolute value of R? Well, that's the absolute value of 3/2. And that's bigger than 1, isn't it?
Yep.
Which means this diverges. Now you were asking if we did the n-term test, right? The first test. If you look at this right here, and I ask you, what happens to this as n goes to infinity? Do you see that that number is bigger than 1? 3/2 is bigger than 1. And what happens if you take a number that's bigger than 1 and start raising it to a bigger power? It's going to go to infinity, which is not 0. So it diverges. So you could have used the n-term test to show that this diverges, but the geometric series tells you it diverges because that's bigger than 1. So I would argue that this is easier. So that's it. Say it diverges, we move on to the next example. Okay, this one, same thing. I'm kind of just laying it out here for you, right? A is 4. What's R this time? 2/3. Okay, so I check the absolute value of R. Absolute value of R is this time less than 1, which means we have geometric series that is convergent. It's a convergent geometric series, and I know what it converges to, right? So this converges, and it converges to A over 1 minus R, which is 4 over 1 minus 2/3, so 4 over 1/3, which is the number 12. So it adds up to 12.
So that's considered the sum, right?
That is the sum. That is the infinite sum. So like we go further and further and further out in that sum, it's going to get closer and closer to 12, like 3.99999. Go a little bit further, you got more 9s, right? And just when things were getting easy, we get this. All right, does that look like this?
No.
No. Do you all see this is different? Everyone see this is different? So let me write this down here. Negative 4 to the n minus 2 over 7 to the n plus 1. Now, the reason I'm thinking geometric here, because you asked about this a minute ago, like what tips you off, is that I've got a number to powers, right? And these powers keep getting bigger. That's what geometric series are like, right? You've got this r to the n, a number to a power. That power keeps changing, right, as n gets bigger. So I'm thinking this is geometric right now. That's what I'm thinking. I just need to make it look like this. So what my goal here is to see if I can get some number to the n minus 1. That's what I need, some number to the n minus 1. So how about if I start doing some tricky things, some fun stuff like this? That negative 4, how about I write that as n minus 1 minus 1? Isn't that the same as n minus 2? Yes. N minus 1 minus 1? I'm just being clever. That's all I'm doing right now. I don't know if you consider this clever, but I'm trying to get an n minus 1 up there. So I'm looking at n minus 2 as n minus 1 minus 1. And on the bottom, I'm going to do the same thing, except this time, I don't have a minus 1 to play with already, so I'm going to have to make it appear. So I'm going to make that look like this. 7 to the n minus 1 plus 1, but I already had a plus 1 down there. So it's kind of like I'm introducing this. I'll do it in different colors. Kind of like I'm forcing this minus 1 plus 1 in there, right? It's the same thing, right? Take it away and add it is the same as if it was never there.